Hello, students! Have you ever thought about what is actually happening when you stir sugar into your tea? Today, we are going to understand the science behind this everyday magic. The topic is solubility. So let's start with this simple question. You add sugar to your hot tea and poof, the crystals disappear. But you keep adding more, and eventually the sugar just sits at the bottom, no matter how much you stir. Why is there a limit? This very question, you see, is the key to understanding solubility. All right, so let's get to the bottom of this teacup mystery. Our first section is called the disappearing crystal, where we will understand the core idea of solubility. So you might be asking, why do we need to study this? Why is it important? Well, solubility is a very fundamental concept. It explains so many things, from how medicines are purified, which is a life-saving application, to why sometimes in the lab you mix two clear liquids and suddenly a solid is formed. We call that a precipitate. Okay, so what is solubility at its most basic level? Just think of it like this. It is simply how much of a substance can dissolve before the solution becomes, well, full. It's a capacity limit, that's all. Now, to help you imagine this, picture the water molecules as dancers in a big, crowded party. The salt ions you add are like outsiders trying to join this dance. The water dancers pull these outsiders in, surround them, and they become part of the crowd. They seem to disappear. But what is really happening when the solution is full? It's not that everything stops. Oh no, it's a very active situation. A perfect balance is reached. We call this dynamic equilibrium. For every single particle that leaves the solid crystal to dissolve, another particle from the solution comes back and sticks to the crystal. It's happening at the exact same rate, a constant give and take. Now, for your exams, you must know the proper definition. So here it is. Solubility is the maximum mass or moles of a solute that can dissolve in a given amount of solvent at a specific temperature to form a saturated solution. Please pay attention to those two phrases, maximum amount and specific temperature. They are absolutely key. Okay, that definition was a bit technical. Let's make it much, much simpler with a very nice analogy. Our next section is called a molecular parking lot. I think you will really like this analogy. It's a very simple and powerful way to understand what saturated means. Just think of solubility like the capacity of a car parking lot. The solvent, let's say water, is the parking lot itself, and the solute particles, like sugar or salt, they are the cars. Now let's map this out clearly. The parking lot, that is our solvent. The cars, they are the solute particles. And what happens when the parking lot is completely full? That is our saturated solution. And what about those extra cars that can't find a spot and are just waiting outside? That is your precipitate, the undissolved solid sitting at the bottom. So why did chemists even come up with this concept? Well, it exists to solve a very real problem. We needed a way to predict when will a solid form, when will something precipitate out of a solution. Knowing this is so important, especially for things like purifying chemicals. Okay, let's build a clear picture in your mind step by step. First, imagine a beaker at 20 degrees Celsius. You've dissolved some sugar in it. The solution is clear. This is an unsaturated solution. Step 2, now you add more and more sugar until some crystals are just sitting at the bottom. The solution is now full. It is saturated. At this exact point, on a molecular level, you have that perfect balance, that dynamic equilibrium. But now for the interesting part. Step 4, you heat the beaker. And what do you see? Those crystals at the bottom, they disappear. Why? Because the hot water's capacity to dissolve the sugar has increased. All right, now let's take this out of the textbook and see where this concept shows up in real life. Our next section is solubility in action, from your kitchen to the pharmacy. Here's something you can practically observe. Let's say you take 100 milliliters of water at room temperature. You will find that you can dissolve about 36 grams of table salt. It all goes in, but if you try to add one more gram, the 37th gram, it just won't dissolve. It will sit at the bottom. But now, you heat the water to, say, 80 degrees Celsius. Suddenly, that 37th gram also dissolves. And the best part, when you cool the water back down, poof, a crystal reappears. This very idea is used in a very important industrial technique called recrystallization. It's how we produce ultra-pure medicines. You take an impure solid, dissolve it in a hot solvent where it's very soluble, and then you let it cool down slowly. As it cools, its solubility decreases, and the pure substance forms crystals, leaving all the impurities behind in the solution. It's a fantastic purification method.
So after seeing the sugar and salt examples, it's very easy to think that heating always helps things dissolve. That higher temperature always means higher solubility. Isn't that what you would think?
Well, actually, that's not always true. And this is a very important point. For most solids, yes, a higher temperature means higher solubility, just like our sugar example. But for gases dissolved in a liquid, it is the complete opposite. A higher temperature means lower solubility. Think about it. This is why a warm bottle of soda goes flat so fast. The dissolved carbon dioxide gas just escapes because it is less soluble in the warmer liquid.
Okay, we have covered a lot today, so let's quickly do a final recap to make sure all these ideas stick in your mind for the exam. So what are the most important things to remember? First, the core idea. Solubility is just the maximum amount of solute that can dissolve in a solvent at a given temperature. Second, the mental image. Always remember that parking lot analogy. When the lot is full, it's saturated. And for solids, heating it up adds more parking spaces. And third, the real-world connection. This is why we can purify medicines, and it's also why your cold drinks keep their fizz much better than warm ones. Just remember these 3 points, okay? The core idea, the parking lot image, and one real-world example. If you do that, I promise you, this topic will feel so much lighter and easier in your exams. And now I'll leave you with one final question to think about. We just saw that temperature affects the solubility of gases, but did you know that pressure also has a very big effect? So, keeping that in mind, how might pressure explain that psst sound and all the fizz when you open a bottle of soda? Think about it. Thank you for listening.